I'm Josh Grindley, and I'm very pleased to be able to introduce our speaker today, who's somebody I've known. I was trying to think when I first met Angela, but I believe, and not that these dates are that important, but I think it's back in the early 90s sometime when Angela was—
maybe even early, maybe even earlier with
maybe even earlier than that.
when I was a graduate student, but who knows?
Okay, it could well be, because I used to, I haven't been to Chicago in a while, but I used to be there moderately often, and it's a wonderful place. But let me finish the introductions here. And the introduction could be very long, but I don't want to take our precious time for a colloquium to take so long, but I will just mention a few milestones for Angela. She's now the the Dean of Science at the University of Chicago. She's a professor in physics, of course, and is I have some notes here. She is, and this is a very distinguished chair indeed for Chicago or any place, the Albert A. Michelson Distinguished Service Professor in the Department of Astronomy and Astrophysics. And she's chair of the department, or was from 2012 to 2017. And she was chair back between 2003 and 2006. So she's done double duty, and maybe that's why she's now a dean. But in any case,
I didn't learn.
well, I'm sure they were grateful. And she's had a very long history dealing with cosmic rays, which we're going to hear, of course, about today. But it goes back to early days. She was the really lead on science for the Auger array in Argentina. So she's had a wonderfully productive career, and today is going to speak to us about two projects that she is leading, POEMMA and EUSO-SPB. I could translate those for you, but I'm going to leave that for Angela to do. And so, Angela, we're thrilled to have you here. Please tell us about what POEMMA and EUSO-SPB are going to do.
Lovely. Thank you so much, Josh and Randall. Let's see, how do I do this? Yeah, this is good. I hope you can hear me and see my slide. It's a pleasure to be visiting. I wish it was in 3 dimensions, but we are now stuck to 2 dimensions. So at least, you know, I can imagine what Cambridge looks like today. I wanted to share with you some of the work we've been doing, and this is, you know, sort of a long-range plan to be able to answer some fundamental questions. And the 2 observatories that I'll be talking about eventually is POEMMA, which it stands for the Probe of Extreme Multi-Messenger Astrophysics, and EUSO-SPB. SPB stands for Super Pressure Balloon, and EUSO is Extreme Universe Space Observatory. So hopefully by the end it will be clear why these different acronyms, but these are sort of related, and the balloon is informing what we would like to build for space, and this is the goal. So hopefully we'll get you to understand all these acronyms. But the most important is, why are we doing all this? And the basic idea is to answer some astroparticle physics questions. And, you know, really astrophysics and astroparticle physics questions, they are related. So one of the main questions that I spent a lot of time on is, what are the sources of ultra high energy cosmic rays? So cosmic rays above 10 to the 18 electron volts are named ultra high energy cosmic rays. And we are very interested in the sources, which are still very hard to see. And therefore, we're trying to measure more cosmic rays, many more, above 10 to the 19 electron volts. And it's a real challenge. We want not only to measure the spectrum of these cosmic rays, but the composition and the anisotropies that they generate in the sky. The other question, which is sometimes related depending on the energy range, is the sources of the astrophysical neutrinos that IceCube has discovered. And again, there is a chance to do multi-messenger coincidence between gamma rays, gravitational waves, and neutrinos. So far, we've had gamma rays and gravitational waves, and we've had gamma rays and neutrinos, but not the threesome. And at the very high energies for the neutrino world, which would be around PeVs and tens of PeVs, these kinds of missions that we are developing would be very sensitive at these energy scales. And then related to this are some fundamental questions about, things that might be happening in terms of particle interactions at energies much, much higher than we can actually measure in, for example, the LHC at CERN in Geneva, right? So we have accelerators going to the TeV scales, while the cosmic rays give us a chance to go many orders of magnitude, 7 orders of magnitude compared in the energy of the primaries, away above the ones we can do on the ground. So what, kinds of things we can test with that. So for example, there are models with supermassive dark matter, ideas about topological defect decays and extra dimensions and things like that. So these are some of the hopes that we can understand the astrophysics enough to know something fundamental about those. Now, everybody knows about multi-wavelength astronomy, and I just wanted to remind you that multi-wavelength astronomy really covers 14 orders of magnitude in either wavelength or energy, if we think of everything as a photon, although radio waves might be hard to imagine that way, but it is 14 orders of energy in wavelength. And if you add the cosmic rays, and cosmic rays, we know they exist much more recently, starting in 1912. And again, it's a field which has ballooning as part of its history. So with the balloon, Victor has showed that the amount of ionization that one could measure with these measuring tools that he had here by eye, and no oxygen, so very dangerous type of experiments, he went up 5 to 6 kilometers, showing that the increase of the radiation, the ionizing radiation, which we now call cosmic rays. So these cosmic rays, when you add to the multi-wavelength in terms of an energy arrow, you end up doubling the energy range. Neutrinos and gamma rays also, so if you have to extend gamma rays past the nuclei themselves, so relativistics and ultra-relativistic type nuclei, both for the cosmic rays and for generating the gamma rays, and the neutrinos are all produced in a correlated way. Gamma rays, obviously, we can observe directly from the source. Cosmic rays are charged. These are nuclei that have charge, and therefore they are bent around by magnetic fields, so it's much harder to be able to see the sources of cosmic rays. And finally, neutrinos point again. So neutrinos and gamma rays are easier to do astronomy with, except for cosmic rays with such high energies that they can bend very little in the magnetic fields, and that they should then point back to where they came from. But neutrinos are sort of the easy in between, because gamma rays get absorbed when they reach very high energies in the intergalactic medium. So cosmic rays and neutrinos are what is left at the very high energies. So we'll talk about each of these, but just to give you a sense, it is a lot of orders of magnitude that we're talking about also in the cosmic ray and neutrino arena. And if you add in the opposite direction, because gravitational waves are bigger wavelengths than radio waves. So if you add those that we have seen from LIGO, advanced LIGO, and hopefully we'll see in the future by LISA, and maybe already seeing something with pulsar timing in the near future, these really extend another bunch of orders of magnitude the other direction. So the whole space for astrophysics is really 40 orders of magnitude long. I really like to emphasize this because it gives you a huge menu to observe the universe in complementary ways, and having multi-messenger measurements really give you a lot more information than a wavelength. Okay, so now onto the cosmic ray. So here's the simplest way of looking at a cosmic ray spectrum. So this is the flux versus energy, and it ranges from 10 to the 9 to 10 to the 20 electron volts, or it's cut off. This is the good news. There's a huge number of energy bins here. So, 12 orders of magnitude in energy. The bad news is it's 30 orders of magnitude in flux, which means that you cannot observe all of that with one experiment. Also, it's unlikely that all of these cosmic rays are produced by the same source. So independent of the source, there's a solar influence at the low energy. So the bending of the curve at the low energies does not mean that the flux of the original accelerator ends, but it means that there are interactions between the cosmic rays and the protection around the solar system of the solar magnetic field. If you go out of or at higher energy, so you get sort of rid of the solar influence, you end up with the majority of the cosmic rays, which is galactic cosmic rays. And that's what we call usually cosmic rays as opposed to anomalous and so forth. And those are, will never be pointing back. So we need to look at gamma rays and other and elemental variations as a function of energy to try to understand the origin, and supernova remnants seem to be one of the favorite sites to accelerate these galactic cosmic rays. And then we have extragalactic cosmic rays, and we don't know exactly when that transition is, but those are the ones at the highest energies that I will be focusing on, which are, to me, the most exciting in the sense that we want to get to the energy in which we pass the accelerators on Earth. Now, the challenge for the very highest energies is the flux, as I mentioned before. The flux at the highest energies is, less than 1 per kilometer square per century. So if you think of building something and putting it in space so that you can see the cosmic rays above the atmosphere, you could do it for the low energy part. But when you get to above 10 to the 13 or so, it becomes really hard to do it with, meters squared to see, for example, the knee. So you end up with, per year. So it's a very, very slow process. So you end up having to be creative about this. And we have a help from the fact that these cosmic rays interact with our atmosphere, and the atmosphere really becomes the first stage of our detector. So instead of catching the primary of the cosmic ray coming in, we look at extensive air showers produced by a primary. So a primary with very high energy comes in, interacts with some atom in the atmosphere. That generates a cascade of particles that by 1937, Piago had already observed and had estimated that the energy of cosmic rays would reach at least 10 to the 15 electron volts. Piago was also instrumental in starting CERN. So, back in the 30s already, almost a century ago, we had evidence for these showers. And it is these showers that we detect. Either we detect them on the ground with detectors on the ground, or we detect an aspect of them. For photons, for example, for gamma rays, we detect the Cherenkov that's sort of focused by the shower of a gamma ray shower. And for cosmic rays, we look at the fluorescence of nitrogen, which is very exciting. So here is just a simulation of a proton shower coming down with 10 to the 14 electron volts. And it's in the first panel, we are following the center of energy here of the interaction. So you see one tiny little proton creates lots and lots and lots of particles. In red is the electromagnetic part of the cascade. In blue is the hadrons, and in green is neutrons, and there are lots of muons in gray. What you see on the right is basically the amount of electromagnetic particles or energy being emitted as a function of height from 20 kilometers down to the ground. And you see that there will be a peak in which it peaks at once the energy reaches a critical energy and the shower stops multiplying, and then it fizzles off. On the ground, we have the distribution from the core. So this is on the lower panel. In red is the electromagnetic part of the cascade, which is dominant. And then we have the muons as the subdominant, eventually the hadrons and neutrons. So this is where we would put detectors on the ground in hundreds of meters to kilometers to detect in coincidence a shower coming in from a very high energy cosmic ray. So the way we can detect it is on the ground or through fluorescence. Fluorescence is generated by these extensive air showers in the electromagnetic part of the cascade. They excite nitrogen, which then fluoresce, and that fluorescence spectrum is well known, is in the UV, and we can design telescopes to observe the UV emission, and that's how we know that this shower happened in the atmosphere. So just to repeat a little, this is the way that the energy gets distributed as a function of depth in the atmosphere. And then in the shower, we have both the fluorescence, which has a really nice property of being isotropic. So you can be very far away from the shower and still observe it. And then you have the pointed towards the ground, the Cherenkov emission, which is beam forward. So this is one way. So for example, the gamma ray detectors that you might have heard of, MAGIC, Veritas, the future CTA, and HESS, they are all observing the green part, which is hardly the sort of pinkish part of the shower, which is the Cherenkov that's pointed downwards. For us, we use the fluorescence because our fluxes are so low that we can't put many detectors within a Cherenkov cone, which tends to be very narrow. So we prefer to observe it from far away. That's how we can handle the very low fluxes. So we built the Piago Observatory with the leadership in Chicago, but with 19 countries, and it's been operating fully since 2008. We started construction in 2004, and the telescope array is in Utah, led by the University of Utah, but again with 5 country collaborations, and these are the largest observatories for ultra-high energy cosmic rays. In Utah, 700 kilometers squares, and in Argentina, the Piago Observatory is 3,000 kilometers squares, and we have these fluorescence telescopes around. So here is a outreach video showing the fluorescence being emitted by the shower, the particles reaching the ground, and yellow are the detectors on the ground detecting the particles. And then the fluorescence telescopes are around the array of the Auger, and the light should be coming from the shower to the telescope, not the other way around. But anyway, somebody inverted the direction. But the point is that this emission is being emitted from the shower to the telescopes, and we can see that at night. So we observe with fluorescence at night, and we observe the detectors all 24 hours. So the ground detectors look like this. So here's one Auger detector on the field. And if you can see well, there will be another one here, another one there, and hopefully you can see my pointers. So this is the array. The distance between them is 1.5 kilometers, and we have 1,660 of them spread over Argentina plain area, which is in high altitude but very flat, so that we can do this 24/7. And then we have these telescopes that overlook the array, and they are open at night to observe the fluorescence emission. Then we can do hybrid detection both on the ground and with fluorescence signals. And that gives us a lot of information. And here is a compilation of all the data recently from 2019 of both the Auger and the telescope array at the highest energies, and then other experiments going down in energy. This is the flux multiplied by 2.7, so it makes it very flat at the 2.7 type of behavior. But as you can see, it's definitely not just a power law. It has a knee, it has a second knee, it has an ankle, and then it comes down. So we are measuring the black and the green at the highest energies, but it connects nicely to the other experiments that go to lower energies. So I'm going to show you a few of these features in the Auger, focusing on the Auger data, which is the highest statistics one. And just to give you a sense of energy, this is a 10 to the 17 would be equivalent square root of S of 10 to the 4 GeV, which is where the PP collisions and the LHC, I put the C before the H, LHC, PP collisions should be labeled. So here's just to give a sense that, the nature is going many orders of magnitude above that scale that we can do in the largest laboratory on Earth. One thing we have discovered with our data, especially with the fact that we can look at anisotropies in the sky, I'll show you in a second, is that around 8 times 10 to the 18, so 8 EeV, an EeV is a 10 to the 18 unit. So this number 8 here onwards, we know for sure that these cosmic rays are extragalactic. It's likely that before that they were already somewhat extragalactic, but we don't know exactly where that transition begins. And this is why we are very confident at the above 8 EeV, is because if you plot it in the sky, you can see a significant dipole. So this is the dipole of the cosmic rays above 8 EeV detected by Auger, and it's a dipole of 6.5%. And it points in this direction in equatorial. In the galactic coordinates, it's in this direction here. So you can see that it doesn't point towards the center of the galaxy, or it doesn't seem to know there is a galaxy there at all. So that's what gives us confidence that it's not a galactic source. And if you plot it in supergalactic plane, it does seem to know where the supergalactic plane is, which may be something to do with the distribution of galaxies or the type of sources, but certainly it is very indicative of an extragalactic population that's generating these cosmic rays. If you reach higher and higher energies, and unfortunately lower and lower fluxes, we start seeing anisotropies which are a little sharper than this overall distribution one. So this is when sources and hotspots show up. So here's now a plot from Auger again of the events above 32 EeV. So, you know, we're now an order of magnitude above, and we're starting to see some granularity and some hotspots, or, you know, very not super sharp yet, very faint distributions, but starting to see some anisotropies that we might be able to correlate with where the sources are. So the way we have our, you know, the most significant 4.5 sigma correlation of different catalogs comes from a starburst galaxy distribution within a, you know, sort of local region, because we should be able to see the local region amplified. Unlike neutrinos, the cosmic rays interact with the microwave background, and they don't make it from very, very far away. So it has to be nearby to orders of hundreds of megaparsecs. AGN also correlate at a 3.1 sigma. So, you know, maybe it's one of these two possibilities, a starburst galaxy or AGN, or a third possibility that correlates with these populations, which is not very clear. And one of the reasons that it is not super clear is that just when these correlations become significant, we run out of data. So the statistics at above 40 EeV is what we are trying to design these space missions to fill in the gap. So the statistically limited part of the spectrum, because, you know, it's where the flux is really low, i.e. we need to observe much larger areas of the well, volumes of the atmosphere, or areas on the ground. And that's why we can't quite pin down what the sources of ultra high energy cosmic rays are. We have this interesting looking flux that bends all of a sudden. So for those who are not used to this, you know, there is a few features. There is this knee, which may be a transition of the galactic cosmic rays, changing from being dominated by lighter to heavier elements and running out of the energy of the accelerator. That might be a second component. This is something that people are discussing for the galactic cosmic rays. And then let's talk about the extragalactic. The fact that the extragalactic would give you a feature as it sort of takes over from the galactic seems quite reasonable. You have two different populations, eventually one will show up. What is not so obvious for those who are not experts is why would the flux turn around so abruptly? So there are two possibilities for that turnaround on the flux. One is that the energy reaches a maximum, and therefore the accelerator doesn't accelerate anything past a given energy, and that's why the flux goes down. Or it could be that the actual maximum energy is much higher. However, the protons or iron or whatever is being produced and shot towards us actually loses energy in the microwave background. So this is what's called the Gzk effect. And let me show you one slide on that. So the Gzk effect was proposed by Greisen, Zatsepin, and Kuzmin back in the 60s, in 66, just after the microwave background was discovered. And what they said at the time, very nice short papers, they said that how protons would not be able to come from any energy. So there will be a limit to a horizon and a limit in energy of cosmic ray protons. And iron too. And the basic idea is that a proton looking at the microwave background, a very high energy proton, sees this as a gamma ray, and it's enough energy to make the delta resonance and produce pions. These pions then decay. But here's the effect of this kind of interaction. In blue is sort of a distance to the horizon of the universe. And there is basically no losses for energies around 10 to the 17, 10 to the 18. So a proton from, you know, at 10 to the 18 can come from as far as our, you know, universe horizon. But as you get closer to 10 to the 20, you start having pair production in the microwave background and in other backgrounds. And then eventually this pion production, which really kind of shuts you off to very nearby sources around 10 to the 20 and 10 to the 21. So this is the possibility of seeing the sources, is if they reach these energies, they should be from nearby populations. So the Gzk kind of forces us to see locally, but as we go to lower energies, we should see the whole universe. So at 10 to the 18, having isotropy seems reasonable. The production of neutrinos and photons due to this interaction is also very relevant, because we can in principle observe the neutrinos, and depending on how easy it is to propagate these gamma rays produced, we could in principle observe them. Depends a bit on the radio background that might shut them off. But the neutrinos for sure should reach us. So the question is, how many of these neutrinos can we observe? These, by the way, these are called cosmogenic neutrinos. And I'm pretty sure everybody knows what neutrinos are. We have enough Nobel Prizes to tell the story. Neutrinos are, in the astroparticle world, one of the most exciting particles, exactly because they don't interact very much, and they can come from anywhere in the universe. The negative part about them is that they don't interact very much, so it's very hard to measure them. So cosmic rays are made of up and down quarks. The leptons in general we can't see, so we are really in the astroparticle multi-messenger world. We are tied to the photons. All of astronomy is up and down protons and the neutrinos. As you know, neutrinos have given us lots of recognition for the astroparticle field or astronomy in the physics world. Starting with these neutrino Nobel Prizes just by observing the sun and supernova 87A with neutrinos, and Davis and Koshiba receives that Nobel Prize. More recently, we had the Nobel Prizes associated with neutrino oscillations. So we all know now that neutrinos change flavors, and therefore, even if a source has, for example, produced only muon and electron neutrinos, as they traverse the universe, they will be arriving on Earth also as a tau neutrino, a percentage of them. And we will be focusing our technique in actually measuring the tau neutrinos. Then we discovered with IceCube that astrophysical neutrinos exist. So we have atmospheric neutrino background, which was used to get this oscillation Nobel Prize winning in research. And then just as the atmospheric neutrinos die off, we have the population that we call astrophysical neutrinos, which are still to be determined. We have one correlation with the blazar, with the gamma ray blazar, but then we don't know exactly what most of the population looks like. And then eventually these cosmogenic neutrinos that I mentioned. So here's the one famous TXS0506 plus 056, which has both a gamma ray emission with magic Fermi observations, and then IceCube observations of the same flare. And this is when, if you look at the transition between atmospheric and astrophysical neutrinos, you get these new neutrino sources which are being generated by astrophysical sources. And we still are trying to understand their origin well, but this is one of those smoking guns. And then the cosmogenic neutrinos that I mentioned before is something that would be really wonderful to observe and detect, so that we can actually understand both the neutrino itself, but also the cosmic rays that produce them. And the problem with that is that Auger has seen a very interesting composition of the cosmic rays. It's not all protons, and the spectrum seems to dive a little bit faster than we expected. So this is now a grand unified view of the particle astrophysics world with the gamma rays coming down here. So this is the gamma ray detections and the cosmogenic gamma ray background produced by these cosmic rays. Here, the cosmic rays at much higher energies in gray by TA, Auger, and Cascade. Then we have IceCube in yellow, the actual astrophysical ones, and then a limit to the higher energies. And here's what we expect the cosmogenic neutrinos to look like now. So much, much lower than originally thought. And that's because the cosmic ray composition is making the predicted cosmogenic production much lower. But if you do have, for example, instead of looking for just the background, but also for a coincidence with something happening in the sky, one should be able to see neutrinos if they are emitted. So Virgo and LIGO saw GW 17070817 and localized it enough for everybody else to take a look. So Fermi and Integral also seem to have found emission from the same area of the sky. And in principle, Auger could have seen it if it was, emitting neutrinos. And for these types of detections, the area in the sky that can be observed is very thin, because the neutrinos need to come at a very sort of glazing, very low elevation, because they interact very rarely. So the probability of neutrinos coming through has to be from a very close to the horizon for Auger, and this is where the GW happened. So there was no coincidence from that detection at the time. But that shows how one can, in principle, do this multi-messenger coincidence of gamma ray, gravitational waves, and neutrinos. And the kind of projects we're working on is to do that above 10 PeV. So let me tell you about the probe of extreme multi-messenger astrophysics. Ultra-high energy cosmic rays and cosmic neutrinos are the two multi-messengers that this is designed to observe. This is the collaboration that we put together with many US institutions and some foreign partners. These are scientists both from different collaborations in the cosmic ray world, like Auger, EUSO, Auger, and TA, and gamma rays like Veritas, CTA, Fermi, and theorists. The idea is to put two telescopes that can do two kinds of observations. So the telescopes would be in low Earth orbit, looking down for this fluorescence emission from ultra-high energy cosmic rays. So the kind of observations with two eyes would give us much more detailed information about the reconstruction of each of the showers. So we know the direction better, the energy, and the composition better. The composition is determined by how high is the peak of that fluorescence emission. And we need two eyes to do a stereo reconstruction. So that's why we like to have two eyes for this part of the story. And by projecting it down, this is actually where I'm from originally, Rio and Sao Paulo. I should have put Boston here, but I didn't have time today. Anyway, but this is about 400 kilometers radius. If you compare it to anything on the ground, this is a much, much bigger area than we can have instrumented by detectors like Auger. And then the other part of our goal is to observe neutrinos. And these would be tau neutrinos that cross the Earth and make a tau lepton on their way out. And that neutrino then showers towards us, basically. So we observe the Cherenkov radiation. It's closer to what the gamma ray detectors do on the ground, but now really focused at the limb of the Earth, looking at a 10 degree below the limb and looking at the emission in that region for these neutrinos. So we would also observe the cosmic rays in the rest of the volume of the atmosphere, but on the limb of the Earth would be really to search for the tens of PeV neutrinos. This is the group of engineers at Goddard, plus the group of scientists that got together for 2 weeks, one to do an instrument design and the other to do a mission design. This is in 2007, and this was all funded by NASA in preparation for the Astro 2020 review, which we are hoping to hear some interesting news, hopefully good news in 2021. This is the product of that effort. So it's two telescopes. These are, mirrors, which are not optical types. We want to see UV light and in Cherenkov optical light, but not with such precision that our exoplanet colleagues need. So it's a very rough measurement with a degree of the actual path, and the reconstruction is within a degree, and the pointing resolution is 1/10 of a degree, and the corrector lens will make it into 0.01, so 1/100th of a degree. And this is the idea is to basically monitor the atmosphere with the largest field of view we could afford, which was a 45-degree full field of view. And this 4-meter telescope would be with a camera here in the middle. So it's a Schmidt optics and a corrector lens inside a shield. And this is opening and closing with a little infrared camera just to help us with the cloud coverage from below. And then I'll spend some time on the camera in a second, but since we wanted two and we wanted to fit into a pro budget, we put both of them in one launch. And to make one launch with two of these, we would have to make them collapse into this basically more, compact form, and then they would be deployed with just knees around each of the units. But to us, the most fun was to design the camera. So the camera is really two types of camera in one focal surface. One which is really designed for the fluorescence emission, and the other which is designed for the Cherenkov emission. So in red, it's a Cherenkov detector, which we haven't flown yet in a balloon. So we're building it now to be flown in the balloon in was supposed to be 2022. With COVID is most likely 2023. And this is the Cherenkov detection of the neutrinos on the limb of the Earth. So we designed it so that the limb of the Earth would be somewhat here below, and we would be observing below the limb. These are the time scales for Cherenkov is much, much faster than for the other side, which I'll explain in a second. And so the Cherenkov needs a sampling of 20 nanoseconds, which is the big challenge, both in terms of being very fast, but the other is in terms of power, so that we have to use very smart triggers to be able to analyze the data and not have to write everything down, because that takes a lot of space. On the easier side of our cameras, things that we have built many of, and we have flown them in balloons, and we have one of these units now actually inside the space station. And this is the fluorescence side. So in the fluorescence, each of these black boxes that are divided up in blues are multi-anode PMT arrays that you show here, a real one in the picture. And these have a microsecond sampling, so slower by comparison, but fast for other standards. And this is a shower would be pretty much within 4 of these units, a typical shower that we would observe. With that kind of design, we can have POEMMA looking at nadir or limb ranging an order of magnitude from 1 to 2 orders of magnitude above what the extrapolation of the ground observatories would look like. So this is assuming that we're not building yet another even bigger thing on the ground. Then, this is the kind of sensitivity we would have to ultra high energy cosmic rays. And we could do, one eye looking at the limb in one direction, one eye looking at the limb in the other, and at the same time doing the stereo vision in the middle to do the 2 types of science. And this is the power of POEMMA compared to the ground-based observatory. So here is in declination, the telescope array in black and the Auger Observatory in green. And here's POEMMA at different energy scales. And it's really built to look at the, starting at 10 to the 19.7 to 10 to the 21 electron volts. We have much, so the brighter, obviously, the more we can see, and we would see further away and have more of an exposure. We simulated what a starburst galaxy type correlation would look like using the Fermilab. And we would easily show way past 5 sigma these are the places where the sources of ultra high energy cosmic rays are, if these are the actual culprits. So we could easily answer that question with that kind of data. On the other side would be pointing towards the limb, looking at a tau decay from a tau neutrino coming from the other side of the Earth. And this is, as you see, you can actually go to lower energies compared to the ultra high energy cosmic rays and start at around 20 PeV or so. And we would be observing the tau neutrino, but generated by E and mu neutrinos on the source, and the oscillation would change them into taus. So here is a table, and this paper, if anybody's seen this before, go back and see it again, because we just updated it. And I think this is now the published version. And it has, basically, we studied many different types of transients to see which transients would be easiest to see with these neutrinos. And it is, neutron star mergers, some black hole merger models that obviously have something in there aside from black holes, otherwise you wouldn't see anything. Some tidal disruption events are also quite luminous in neutrinos for our observatory. And then there are others which you would have to be a bit lucky to see. And here are 2 examples. So if you look at neutron star binary coalescence, the Feng and Metzger predictions show that within a week they would have their peak flux. And POEMMA and GRAND, which is a proposed radio array, a very, very giant radio array in China, would be having similar sensitivities just when the peak is happening. So for these kinds of events, we would be very well placed. IceCube Gen 2 is likely to be able to do a good job too. This is going to be a long road there because it's a much, much bigger version than IceCube. However, you know, we think of these things as really worth doing both, because it's very complementary in terms of distribution in the sky. And I'll mention this in a second. And this is for a different, so these are, you know, long and short bursts. And by long, we mean, you know, some things have happened very quickly. We can turn it around within minutes, and others we can see for months later, depending on the model. But I'll give you a little more detail on the POEMMA orbit itself. And here is another type of short gamma ray burst type models, in which, again, we should be able to observe them. Depending on the types of emissions. So what I mentioned before, the complementarity between us and IceCube Gen 2 is that IceCube is stuck in the South Pole, which makes it the coverage of the sky very limited. These very high energy things are coming very close to the horizon. So you are observing the horizon as the Earth turns around. If you could build IceCube on the equator, you would see the whole sky. But since it is down in where the ice is, they have not a huge amount of freedom in looking at the sky. So it has to be lucky that the sources land within this band, while we in space can see the whole sky, which is very helpful also for ultra energy cosmic rays, although Auger and TA together can see the full sky, one and the other by themselves they can't. Seeing the full sky with the same observatory is really helpful, as there are some systematics between experiments. So here's you know, how POEMMA would be looking for these neutrinos, basically observing the limb and looking for things that are coming from below the limb. And an orbit is 94 minutes or so. And you can, within 94 minutes, be looking in any direction you want. You could actually do it even sooner. We only see half of the sky because we look at the dark side of the sky. The Earth going around the sun. So if something is bright for a longer period, then the fact that we're going around the sun means that we have full sky coverage. But for very, very short bursts, we can only see half because we need to be on the other side of the sun. Although the source could be on the side of the sun, because the sun will be lighting the side that we observe, but the neutrino will be coming from the other side. So the neutrino source would actually be aligned with the sun. Okay, so POEMMA, to summarize the POEMMA part, and I'll be quickly just showing you what the balloon looks like. The POEMMA will be opening these two new cosmic windows with neutrinos above 20 PeV and extreme energy cosmic rays above 20 EeV. And this would be an order of magnitude improvement compared to the ground in sensitivity and wide range of energies. And in principle, we would be able to study these extreme accelerators. Now, the EUSO part of the story is that we have a collaboration that's been ongoing since 2000 or so. And it was named Extreme Universe Space Observatory, the first version of it. And then there was a study that made to put things in the JAM, which is the Japanese experiment module. And that didn't work out in the long run because the Japanese stopped taking big things to the space station. So we changed the JAM into joint experiment missions, because we have been together putting, you know, many different types of detectors all over the place to prepare for something like POEMMA. So so we've done a few balloons, and the last one is Mini EUSO, which is here in the cosmonaut's hand, which is part of the space station. And I'm going to just flash you very quickly. We did one balloon flight back in 2014 to test how these detectors would work with fluorescence, and they work quite well. And we did another balloon flight called EUSO-SPB 1 for a super pressure balloon. And this is now us in Wanaka, New Zealand, trying to have a very long time scale flight so that we could get a lot of data. We launched in 2017 in April. Unfortunately, there was a leak in the balloon and it didn't go very far. So we ended up in the Eastern Island. But the idea would be to have been going around and around. But after 3 days, we were not super successful. So we're building another balloon. So compared to the previous super pressure balloons, we had a very short flight. But we are now building the next SPB. So it's SPB 2. So I already mentioned Mini EUSO. Here's the cosmonaut, and this is SPB2, which will have a Cherenkov detector looking towards the limb of the Earth and a fluorescence detector looking down. So we split the POEMMA camera into 2 cameras, into 2 telescopes to show that those 2 techniques work very well. and we are building it right now. So we're hoping to launch. So this is some of the pieces of the detectors and the mirror elements that are being put together. And this is what we're trying to launch. We were planning on 2022, but we are now estimating more likely 2023 campaign. This would be in the spring in Wanaka, New Zealand, and EUSO-SPB 2 would have both the elements that we propose to build for the space mission POEMMA. So thank you very much. This is all I plan to say. I just will let you see this thing without volume. Hi, Josh. I saw you show up at some point.
Okay, yes, I'm here, and this is very exciting. How do you get for the fluorescent component where you need to know the atmospheric depth? If you're looking at events on the limb, you need to be at 90 degrees from that, I would have thought.
Yeah, so the limb is really for the Cherenkov flash coming towards us. And we would be observing, if you have two eyes that have a little bit of distance between them, we would see the fluorescence on the near field. All the way to the limb would be monotype detections, right? So we would see both eyes, but not enough of a separation. So we would have an estimate of what the energy is. And the distance, one can do an estimate basically because you have the probability of it being at a lower altitude than above you, right? So you have, well, if you're in space, the balloon is definitely below us. But in space, it's very, very far, the atmospheric densities we put a probability of it being at this distance from us. And given the light, we can do all the reconstruction. So it's not as precise, but it's a good way to do statistically measure all these things.
Good. Well, so this talk is open for questions, and I'm going to look for hands raised. Or Randall, are you going to handle that and call on people?
I can do that, and
because I don't see any hands raised, and I'm looking at the attendees, obviously, just to see if
Charles has raised his hand.
Okay, Charles, please go ahead with a question.
Okay, hi Angela. Thank you very much. This is Charles. I was actually
Charles, how are you?
I'm fine, actually. So good. Thank you very much for visiting us this way. I have a question actually going way back to the early portion of your talk where you showed the all sky distribution of the Auger detections. And I was just wondering just how small a number of distinct sources might actually account for that, because it looked like you might have as few as only 2 or 3 distinct sources there.
Yeah, it could be. So this is the trick, right?
Oh,
so
we
have,
yes.
We have these, hotter spots, and we don't know what populations they are. But if you put the populations that, so we don't expect too many AGNs within 200 megaparsecs. So those are the nearby AGN, and the distance that we are estimating is proportional to how likely it is for the composition you observe to have sources further than that. And that's very unlikely. So you end up having sort of a maximum distance or a sort of dying down. A more powerful source further away can be contributing to. So you have to, include the fact that the propagation will enhance the nearby sources compared to the faraway sources, which is not true for neutrinos, for example. And then once you're done with looking at distribution, so in the case of the AGN is the gamma ray emitting AGN, which is not everybody, and that's this correlation that's of 3.1. And then from the starburst catalog, again, it's not very far away starbursts are the nearby ones. It's about 4.5 sigma. So it's not a lot of people. Which is why I can put names on them.
Yes, okay. And while I've got your attention actually, and my hand's still up, how high does your super pressure balloon actually get to?
Yeah, so it's 33 kilometers.
Oh, it's way up there.
Yeah, and the idea, so let me do a little NASA balloon propaganda here, because I love that. I think small sats are another really good way to go. But these guys take much bigger pieces of equipment up. before we spend $1 billion, right? So here is it in feet, if you like, 110,000 feet. And this is the idea, if it were working well, so if it didn't have a leak, it would stay like the first few days completely straight. So the super pressure part makes it, so it's helium super pressurized, so it doesn't go up and down like it did if it's not leaking. So it sits still, and it could go for 100 days or more, and it could reach, for example, from Monaco to, say, Chile in 4 days and just keep rotating. This is a map of the winds, and the winds in white in a time of the year. So the winds change a lot depending on the time. But for, say, June 17, this is when I took that picture, then you have 100 kilometers per hour here. So it's very nice and steady, and it comes around, so you can launch the balloon and sit there for quite some period of time. So that's the dream. And as I mentioned before, so the COSY had a very nice, turn around on eddy here and then came around. And then again, I think they had a leak when you see a very erratic way of moving around, is likely that you went to lower altitude and the winds are very more turbulent, so you end up in a random walk. But if you're high enough and steady, you should be able to go in circles around. So the super pressure balloon is not quite finished. It's R&D, and we were an R&D payload. So we signed off our $30 million payload to be dropped in the middle of the ocean. A little sad.
So Weston, you have your hand raised.
Okay, thanks, Josh. Yeah, so I was noticing on POEMMA that the energy range of these neutrinos was on the order of 20 PeV, which is about a factor of 100 brighter than the famous neutrino that came out of IceCube that was seen by all these gamma ray telescopes and sort of launched, in some sense, neutrino astronomy. And as you get into this neutrino business, the fluxes drop dramatically as you start going up, and it starts to become important how well you can sort of reconstruct these things. And one of the things that's challenging for IceCube is they say, well, we find this thing, it's in a general direction, and you can either do these sort of statistical buildups like Charles just kind of referred to for Auger, or you say we see something, and how well do we find it, and can we point these telescopes? And can you kind of just sort of give a feel for how well POEMMA might be able to resolve a neutrino, or how long it might take to integrate? So we have something to follow up on. Right.
So I think that we need somebody else to tell us where to go. So this sort of approach of target of opportunity, we need somebody to say, look in some direction, because the idea. Let me go back a little bit to the challenge in the flux side, which is what you were mentioning, right? So. When we started designing POEMMA, we were after the cosmogenic neutrinos, actually, and that would be a diffuse flux, and we just integrate, look in any direction, and keep adding. But it turns out that with the composition of Auger, the cosmogenic neutrino has gone down quite a bit compared to the first time we calculated these things. And then, so it's a lot easier to look at these neutrinos in the sense that they should be there. So the problem is, as you can see here, the astrophysical one, maybe it's even clearer, maybe here. So the crossover from the crossover from atmospheric starts just below the PeV, right? So when you are at 10 PeV, so we would be starting here when IceCube sort of, ends. But we're using a lot more, volume of the Earth, right? So the comparison for us versus IceCube in terms of target, current IceCube, is that IceCube is a kilometer cube, and we're looking at the limb of the Earth using all of the Earth below that limb, 10 degrees down. It's a lot of material. However, what we observe is just a Cherenkov cone coming at us, right? So they have these strings so they can get the path a little more precise, but not super precise either. So you can see here on the declination, my image is on the ray. You can see that, it's one can point, but not super well. So in our case, the limitation is the neutrino makes a tau, the tau makes a shower, and then we have a Cherenkov cone. The Cherenkov cone is about 1 degree opening. So even if we measured everything about it, we would still have 1 degree out there to point to. But that's enough if these are rare events, like a gravitational wave event. But it's not, and then we need to follow up, right? So we can follow up within a few hundred seconds. We can point in any direction in the dark sky. And then we can wait if it's going to be something that peaks later. So some of the models that we compared, they peak a little later. And in those cases, you can wait a little longer. So they're long and short bursts. The peaks here you see are around the energies we're talking about. And here is in blue, 10 to the 5 to 10 to the 6.5 seconds. And in green is a little earlier. And this is because in this model, it's 2 neutron stars making a magnetar, and the optical depth to neutrinos in the beginning is really not very big. So it becomes actually brighter a week later. And so that's easy for us. And anybody who's monitoring will be looking in that direction if they can. Most of these other detectors cannot go anywhere. So they just sweep through and then see if something came from that direction. And the challenge for those in the South Pole or North Pole is that they don't see most of the sky. So if this is in the wrong place, there's nothing you can do. But if for us, we could see all the sky throughout a few months, because the dark sky will become the bright sky and vice versa. So for half the sky, we can see easily within weeks or even within minutes, right? So this is the plus of having something in space. But you see other models come to lower energies, but they always have some emission in 10 to the 7, 10 to the 8 GeV. I'm not sure I answered your question, but did I?
You got a good bit of it, and I think the main thing I wanted. So
yeah.
Yes.
So here, for Auger, this event is very much in the horizon to see neutrinos, because you need, again, neutrinos don't interact. So for us, we're using the Earth, right? So we're using it coming up from the other side of the Earth, crossing the Earth and forcing it to interact and then decay. While others need to do other tricks. So in Auger, what we were doing is basically looking at showers, which are very, very inclined and develop very close to the detector. Basically, they cross most of the atmosphere without showering, because otherwise there's tons of protons there. So for each neutrino, you would see a lot of other cosmic rays. So to select a neutrino out of everything else, it needs to be a very deeply penetrating shower that did not finish its own thing way out there, because the atmosphere is 36 times thicker in the horizon versus the vertical side, if that makes sense. Yeah. I'm pointing in a little box, so probably not communicating my directions super well.
That's great. Thank you.
Other questions?
Actually, I had one, just wondering, were there any types of sources with POEMMA that you could test things like Lorentz violation or put limits on neutrino masses?
Yeah.
Yeah, I think that to do the neutrino masses part, the interesting part is the tau versus the other two, right? So we would need to compare what the tau predictions are and what we observe compared to everything else that's done. So that's why we need to do in partnership with people like IceCube, so that we have all 3 flavors. And if we can see all 3 flavors from the same event, then there's very interesting physics to be done. So by the tau by itself, it would be very hard. I mean, you can compare certainly the time it took for the gravitational wave, the gamma ray, and the neutrinos to come. But neutrinos, just like in this neutron star model, this one, the Fang and Metzger, they get a little delayed. So we can't do the measurement of, when was t equals 0, because they're stuck inside for a little longer. So it will have some astrophysics as usual, but I think the answer is yes, but you need to know a lot of astrophysics before you can do the physics.
What is the delay for that Fang and Metzger?
That would be very small compared to weeks. Yeah.
Okay.
Yeah. Oh, you remember supernova 87A, right? That was a small, very small effect that one could limit. But this is, the astrophysics is giving you a much, much bigger delay.
Okay. I was very impressed with your Auger spectrum, which I guess I haven't seen in a while, with
I'm glad.
with the spectacularly small error bars,
Yes, aren't they
particularly out
great?
there at the ankle, so-called. I mean, that was incredible.
Yeah, I am very impressed myself, and
It's
it's
just
so
absolutely
nice
beautiful.
to know it so well, right? So
Yeah.
it's a lot of structure, and one would not have guessed it, certainly not the second knee.
Yeah.
And also how fast it goes, you know, just past here. All our models had a much different shape. So, and the reason this is, I didn't get into details, but the reason this is a little weird looking is because it's a lot of different elements coming in and out. So the story is a lot more interesting. I wanted to get to the future, so I didn't spend tons of time.
I thought the composition was still not that clear. Now you're saying that.
It's a lot. I mean, there are this issues between collaborations, but here's sort of the best guess back in a year ago of the composition trends. And so in red is the proton, and you see it has definitely a knee before the blue being the iron knee. This is galactic stuff. And then, I mean, we don't know, but we expect this to be galactic. And then there's a second proton bump, which could be galactic, we don't know. And then this is the extragalactic bit over here. And you see that the extragalactic bit after the ankle has oxygen, helium, some iron with error bars, some proton and some iron, right? And that's why it looks really strange. It looks flat when it should be, if it was one element only, it would go up and down, and it would look like the green and not like the black. But it is a bunch of different elements coming in and out. And this is, there are error bar issues, which is what's shown in this plot too, the bands. And those have to do with reconstruction and basically cross-section measurements at CERN. So, you know, we try to be independent at CERN, but it's very nice to get the kind of measurements of what kind of evolution of the showers would look like. Because after the first interactions, very quickly, these showers have the energies are lower. And so we can test the whole hadronic interaction models at CERN, and that's what gives us these error bars. And those are getting better too.
Great.
Crosstalk between the two communities.
Yeah. So I don't see any hands raised. Does anybody want to just shout out something, a question or a comment? Because if not, I want to, here's Charles,
I think it's
got your hand up, and so does Martin. So Charles, you want to go ahead?
Sure. Yeah, I'm very intrigued by this figure you just got up with the iron, oxygen, helium, and protons. Is there any model which could account for that range of abundances between the iron and the oxygen and the protons?
Yeah. So yes, but you know, how many parameters can we play with, right? So the challenge, the biggest challenge, is that we are talking about at least two components, right? So the sort of galactic cosmic rays down here and the extragalactic ones. The sample of the extragalactic is very small in number of energy bins. And we have this other bump. So the hardest one is this bump here in the middle, which people are now discussing many galactic type sources that could do this too. Maybe the Fermi bubble, some other, you know, super bubble type acceleration site, which is not the traditional supernova remnant acceleration. So this is active way of, you know, trying to understand this. And so getting rid of this from the conversation, the easiest way to me is to come from the opposite extreme. And we know that iron is it, right? That is, we're not going to see a lot of gold, although, you know, the neutron star coalescence is all about gold. So we are really, iron is sort of the most stable, the most sort of the end of an injection spectrum of an extragalactic source. And so if the source itself has a interesting composition, and we divide it into these 4 bins of the source composition, and you put a power law spectrum and you propagate everybody, and now that you propagate, the protons and the iron are the ones that are going to live the longest. Oxygen will live a little less, and helium will live even less for a given energy. And that's because the protons have this, interaction with the microwave background, and they lose energy. But the iron will be photodissociated, and so will the others. And the iron will show up with higher energy because basically it has more nuclei, and per nuclei, it's sort of similar energies. So you can put all these things in, which is what we did way back then, and do the propagation. And then with one injection spectrum, you can fit all the colorful lines above this ankle. The problem is this other red part. So if you ignore the red, meaning if you ignore this other component, we can do this okay. And if you look at oxygen, is sort of the easiest one to say, well, there's a new component coming in and dying off, a new component coming in and dying off, and a new component of helium dying off. And these, the maximum of each of these peaks are related to basically the Z of each of the elements, because the same accelerator will tend to accelerate to a maximum energy, which is proportional to Z. So that explains, helium, oxygen, and iron. Proton is a bit odd. And so that's where the things get funny, although you do have secondary protons from the heavy stuff falling apart, but not to the level that it would give you the SNE. So this is one of the things. Is it, secondaries, or is it really a new source? And then what source is it? So that's where the field is debating this piece versus that piece. But as you can tell, it's, 3 components. We can definitely explain anything, but why would we have 3 components is the good question, right?
Thank you.
Martin, if you're still there, you had your hand up, but I don't see it up now.
Hi there, yes.
Oh, good.
And Angela, fascinating. For POEMMA, I wondered, you chose LEO and a 4-meter aperture, and I wondered if that was constrained, was that optimal, what you'd choose if you could launch anything, or would you go for a higher orbit and bigger primary mirror, or would you go for
bigger primary mirror? So certainly the orbit, the lower the better, right? Because we want to see, we want to see the atmosphere. So we want to be as close down as we can. And this, the 500 kilometer choice is just so that we don't decay very quickly. But we are happy in the space station, for example, right? Because we want to, our signal is in the atmosphere, so we want to be closest to the atmosphere.
But you might want to be higher to get a bigger area of atmosphere.
Right, so we tilt because the further away we go high up, the closest showers become further and further away. And we want to see, let me close this. We want to see the closest showers in nadir so that we can do really precise measurements. And then towards the limb, we will see a little bit less precise. But let me show you one cute picture. Behind all these people, there is a much, much bigger mirror. We started with a 6 meter and it got to be $2 billion. And the cap for probes is 1. So we went down to 4. So definitely a bigger mirror. And so the primary mirror we would do as big as we could possibly carry with the money, the boundary conditions financially. Now, one thing that would be really nice for us is deployable mirrors, because we are not, as I mentioned, in the diffraction level. So we don't need the precision that optical astronomers do. So we could use a, not great surface mirror, but very, very large. So we are happy to have deployables, even if they're not hyper precise. So we are talking about, maybe designing something smaller just to try these, to look at the Cherenkov with deployable mirrors.
Great.
You might even be able to do that from small sats.
Yeah, that's what we'll be working on as soon as we finish the POEMMA paper, which should be this year.
Good. And Ramesh. Ramesh has a question, it looks like.
Yes, okay, great. Yeah, thank you very much. That was a really interesting talk. But if we go back to that Schroeder 2019 plot that you were showing earlier, it looked as if at the highest energies, there is some discrepancy between telescope array and Auger.
Yeah.
which is much larger than the error bars. So what's going on
Excellent.
there?
Right, it's called systematics, which
Systematic.
is one of the reasons why we like the space mission that sees the south and the north with the same data. So if you, this is what you're referring to, which is good eyes, or maybe you heard this, the two groups screaming at each other in some meeting before. But you know, there is two effects. So in green is the telescope array, and they certainly have less, I mean, they have less area on the ground and less time, so they don't have as much statistics. So their error bars, if you compare bin by bin, are becoming much bigger earlier. So there is some, you know, discussion of what's happening here at the highest energies. But even for the ones with low, you know, with high statistics and small error bars, there is an overall shift. And this is why we put this 14% energy scale arrow here. So they use a very different way to reconstruct the energy of a shower than that we do. They put the, you know, the actual hadronic models inside their reconstruction. We reconstruct everything without using any assumptions about the hadronic model, and then we just give the hadronic model after the data. So we do reconstruction by just light as a function of, you know, zenith angle and or, you know, depth in the atmosphere. And then we do a different calibration of what is that amount of light in terms of particles, right? So for fluorescence, for example, fluorescence is the easiest one to get a good energy scale. So our the way we choose the fluorescence and the way we do the reconstruction tries to minimize the hadronic models. And that's why I don't think I have a plot here, but there are many different models that one can compare the result of the Auger composition. For the telescope array, they use the QGIS-JET type models early in their reconstruction. So there are two effects that might be contributing to our, you know, difference. One is the overall fluorescence, air fluorescence scale. For a given amount of particles, how much light should we see? And the other is their reconstruction itself. We are probably in much more agreement than we were early in this game. So this, you know, and by the way, this is what our, you know, energy scale error bar looks like. So the whole thing, the whole black point should be moved, could be moved up, or all of the green points could be moved down in that direction, because this is flux multiplied by energy to the 2.7, and this is versus energy, so that it goes in a diagonal. So you can put one on top of the other, which is what I would expect to be reality. So nature should not have differences between the northern hemisphere and the southern hemisphere like the green and the black. However, when you put the two on top of each other, you still have more flux in the north than in the south. And this may be because of the large scale structure, right? So it is very possible that this plus that gives you more flux where we don't see in Auger. And the telescope array has a hot spot also in the north, which is hotter than the hot spots in the south.
That's fantastic. Thank you.
Yeah, beautiful. Okay, not seeing any other hands, although Ramesh, your hand is actually still up, but no, now it's not. So I think that this has been a wonderful talk, Angelo. Thank you so much. And if we could all clap, we should. But thanks very much. Beautiful work.
Thank you, Josh. Stay all well.